Okay, we're also going to note that the Christoffel symbols do not transform tensorially. So let me just show you the transformation law of the Christoffel symbols. Now this is an exercise Professor Wang posed to the reader, and I haven't completed the exercise yet, but I plan on doing so. So you can see here, we have the Christoffel symbols in a different coordinate system, okay? And we need to understand the coordinate transformation law. Well, it turns out that there's a piece of the coordinate transformation law which is tensorial, okay? So that means that these coefficient functions are going to be independent of the choice of coordinates, but there is also a piece which is not tensorial, okay? So this is very important because the Christoffel symbols themselves do not transform like tensors, okay? Christoffel symbols themselves do not transform like tensors. And this is kind of a reflection of the fact that, you know, the covariant derivative does depend on the curve that we choose. But the covariant derivative should not depend ultimately on the coordinate system. And so this is kind of a problem. So I want you to think about, okay, the Christoffel symbols do not transform like tensors. But wait a second. We kind of need the covariant derivative to be independent of coordinate systems. So why is this the case? And it turns out that, okay, think about it for a second, pause the video and see if you can answer the question. Why is it okay that Christoffel symbols do not transform like tensors? The second term here is what's non-tensorial. It depends on, it's going to produce a transformation law, which is going to mean that these Christoffel symbols essentially um, are not going to, they're going to somehow depend on the second derivatives of this choice of coordinate systems. Okay, which is kind of bad. We don't like that. That's not good. Um, in particular, um, it's going to cause this. It's going to cause the. I guess. Okay, I don't want to just follow the notes. Like, think about, pause the video and try to answer the question. Why is this term bad? Why does it cause problems? Uh, and also, why is that okay? Then how does this definition work, right? And my answer to you is that, first of all, I'm still studying this, so I'm still trying to figure this out. So let me know in the comments if you have any comments about this. But right now, what I can tell is that we're trying to make sure that the covariant derivative itself, and of course these Christoffel symbols are, of course, the coefficients with respect to some coordinate frame, but we want the covariant derivative of a vector field x in the direction, or yeah, in the some in the covariant derivative of a vector field y in the direction of another vector field x. We want this map to be tensorial in the first argument, but it has to obey the product rule in the second argument. Okay, and so in that in that sense, um, right, this is not like the covariant, essentially, parallel transport along two different curves is going to look differently. And also the the covariant derivative of a vector field along two curves which are first order, which agree to first order. So they're first order, what was the term that the author used here? So they're covariant derivatives that are first order oscillating. Okay, so the covariant of a vector field along two curves which are first order oscillating will agree to first order, but it's not going to be identical, right? And I believe that if we had the tensoriality in the second argument, we would have something that which was identical. So I believe that this transformation law is to preserve is to make sure that we preserve the Leibniz rule in the second argument of the covariant derivative. This is an important fact that the covariant derivative there is a certain locality which is satisfied by the covariant derivative. Namely, we have full tensoriality, so full tensoriality in the first argument. But in the second argument, we have that if two curves, yeah, we can actually read these locality statements. I think I needed to read these anyways. So the statements of locality are essentially, this is the locality that we get. I don't want to emphasize, we do not get tensoriality in the second argument. Since it's not a tensor in the second argument, that's part of the reason why these Christoffel symbols do not transform like tensors, okay? Okay, so let's state the locality of the linear connection, okay? So I'm just going to read this. So, um, so the first locality is that for any open subset U of the manifold, if two vector fields agree when they're restricted to that subset, then, and if x, so if x restricted to U is equal to x tilde restricted to U, and y restricted to U is equal to y tilde restricted to U, then d of x y restricted to U is equal to d of x tilde y tilde restricted to U. Okay, so we have locality in kind of a scheme theoretic sense, where if we restrict to an open set and we have agreement on some open set of the two vector fields, which are the arguments of the covariant derivative, then the output vector field will agree on the open set. Okay. Then we have the second locality principle, which is tensoriality in the first argument. So if two vector fields x and x tilde agree at a point P of the manifold, just at the point P of the manifold, then the covariant derivative of vector field y in the direction x at the point P must agree with the covariant derivative in the direction x tilde of the vector field y at the point P. So this second locality argument is a pointwise. It means that the covariant derivative, the first argument, the direction vector field, the covariant derivative only cares about the pointwise evaluation of that direction vector field. It's tensorial in the first argument, so that is critical. And then the third proposition, the third locality characterization of the linear connection is that if we have a smooth curve gamma parameterized on our manifold, let's say from negative epsilon to epsilon into the manifold, okay, such that gamma of 0 is equal to p and gamma prime of 0 is equal to v. Okay, so we've specified the initial point of the curve and the initial tangent vector to the curve, p and v respectively. Now, if we have vector fields on M, we have a direction vector field x such that x at the point P is equal to v. Okay, so x at the point P is the tangent vector to our curve gamma. And then we have y and y bar, which are two different vector fields, such that y and y bar agree on gamma of t. Okay, so if we restrict y and y bar to the geometric curve gamma of t, where t runs from negative epsilon to epsilon, then these two vector fields agree. Okay, so they agree in some neighborhood. They agree along the curve, basically in some neighborhood of the starting point of the curve. They agree completely along that piece of the curve. Okay, then the covariant derivatives coincide at the point P. At the point P, the covariant derivative vector fields coincide. So that is nabla x of y at the point P is equal to nabla x of y bar at P. Okay, or dxy at P is equal to dxy bar at P. Okay, so let me just state this again. If we have two vector fields along a curve such that at the point P, which is gamma of 0, these vector fields agree along some neighborhood of the curve. Okay, so not some neighborhood of the manifold itself, just some piece of the curve, basically. Gamma of t, where t varies from negative epsilon to epsilon. If they agree along some small piece of the geometric curve which contains gamma of 0, then the directional derivative at gamma of 0 in the direction gamma dot of 0 of the two vector fields will agree. Okay, so at the center point, gamma of 0, right? So this is the third locality principle, and it's extremely important It's not full tensoriality in the second argument, but it is kind of if we have it's stronger than just this locality 1 where we force the two vector fields to agree in a full-blown neighborhood. Here we just need a neighborhood of the curve. We just need a neighborhood of the geometric curve. If the two vector fields y and y prime or y bar agree on just a neighborhood of the curve itself, then the directional derivative in the direction gamma prime of 0, not in any direction, in the direction gamma prime of 0, the directional derivatives of y and y bar will coincide at the central point P of the curve, okay? So again, this is a very strong locality statement, but it's also not full tensoriality. So it's very important to understand the exact statement of this locality principle and to kind of meditate on it and recognize what kind of locality this gives us and what it doesn't, okay? All right. Yeah, that's going to be it. Now, yeah, just think about, okay, we have the center point of the curve P, which is gamma of 0. We have gamma prime of 0, which is V, okay? And then the two vector fields y and y prime we're differentiating in the direction V at the point P, according to our affine connection. We're differentiating in the direction V at the point P. That's why we've chosen our curve gamma in this way. If the two vector fields that we're differentiating, y and y bar, agree on some neighborhood of the geometric curve, some neighborhood of the point P of the geometric curve as a one-dimensional submanifold, not in some neighborhood of the manifold, just in some neighborhood of the curve, viewing it as a one-dimensional submanifold. If these two vector fields agree on the geometric curve itself, then their covariant derivatives evaluated at this central point gamma of 0p, those covariant vector fields or the covariant derivatives will agree. And again, the covariant derivatives in the direction v evaluated at the point p of these two vector fields which agree on a neighborhood of the geometric curve centered at gamma of 0 is equal to p, the covariant derivatives of these two vector fields y and y bar in the direction v evaluated at the point p must agree. Okay, so this is the third locality principle.